Okay, welcome everyone. We're going to look at how to find eigenvalues and eigenvectors for 2x2 matrices. And this is again related to what we're doing in our differential equations course here, because we were studying linear systems of two equations, two unknowns, and when we convert that to a single vector equation, the right hand side function here, a, or right hand side, which we normally would call f of y, is really can be seen as the matrix multiplication with the coefficient matrix capital A and the unknown capital Y, where A is the 2x2 matrix with little a, little b in the first row, little c, little d in the second row. What we did starting this section out was look for the simplest possible solution, which are equilibrium solutions or constant solutions, and we were led to two possibilities. Either the only equilibrium solution is the origin, the single constant solution, which is a single constant function, which is the origin, and the determinant of the matrix of coefficients A is non-zero, or the determinant of that matrix A is 0 and there's possibly other non-zero equilibrium solutions. Now the first possibility, in the first possibility, y of t constantly equal to the 0 vector, or the vector valued function 0, 0, that always works for any linear system. So we're going to that's always a solution, so that's not telling us anything new. We're mainly going to focus on that first possibility where the determinant is non-zero. Okay, focus on that now. The case where the determinant of the matrix of coefficients is 0, we're going to handle that in our later work. So for right now, the only equilibrium solution is the origin. Then we went on from there to look for straight line type solutions. We've seen solutions to systems whose graphs lie on straight lines in the phase plane, and we saw such in a previous recording by looking at a harmonic oscillator, doing the reduction of order technique, and then looking at the corresponding graphs in the phase plane. Alright, now we've also talked about linearity principles. Alright, if we have two solutions to the same system and they have independent initial vectors, then we can form a general solution by linear combinations. That is, meaning if we have two solutions and say y1 and y2, these are vector valued functions that are a solution to your system, and the initial vectors at t equals 0 are linearly independent, then and again, what that means is they don't lie on the same line through the origin, then a general solution, I should say not the general solution, but a general solution, because there's more than one way to write out a general solution, but we're talking about these fixed solutions that we are given or have found that are independent initially, and then we can build a general solution by taking sums of scalar multiples. So a constant k1 times y1 plus a constant k2 times y2. And that being a general solution means we can solve any initial value problem for that specific differential equation. So that's a solution, and moreover we can enforce the initial conditions by finding those constants k1 and k2. Now, if we can find those solutions, again, we've already said that we'll be able to find a general solution. This tells us that we should reverse that and look for straight line solutions, and we did this in a previous recording, so it makes sense to look for vector valued functions whose graphs lie on straight lines, and one way to write these out would be to take a scalar function of t multiplied by a fixed non-zero vector, which I'm calling capital V. All right, and what we do is just take that result, plug it in to our system, and see what possibilities are there for the vector v and for the scalar function g. We did this in the previous recording, and what we found was the first necessary condition was we would have to find a number lambda such that a times v, av, is equal to lambda times v, and lambda is called the eigenvalue and v is a corresponding eigenvector. So we call lambda an eigenvalue and v a corresponding eigenvector for the matrix capital A. If we can find an eigenvalue and eigenvector pair, then the function g of t, it turns out, is forced to be not just any type of function, but actually exponential, and the exponent on that exponential is lambda t. So g of t takes a certain form. That form results from solving a certain first order differential equation. So if we can find these appropriate eigenvalue, eigenvector pairs, we will have straight line solutions. If we have a matrix which has two distinct real eigenvalues, then we will have, it turns out, two independent eigenvectors, and therefore we will have two solutions whose graphs lie on straight lines with independent initial vectors, and therefore we'll be able to write out a general solution. Alright, so from here what we need to get good at is finding eigenvalues and eigenvectors. So that's what we're going to practice with next. Alright, so I'm going to go over and do a couple of examples with that. So we're not going to, in this recording, get to actually solving any initial value problems. We're just going to get good at finding eigenvalues and eigenvectors. Alright, so what do we need to look for? We need to find non-zero vectors v such that a times v is equal lambda times v. Now by doing vector subtraction, we can subtract over lambda v from both sides, and that gives us the vector equation a v minus lambda times v is equal to 0 vector. Alright, now we're going to rewrite this left-hand side by remembering that there is a special matrix called the identity matrix, and it's denoted by capital I. And that plays the role of the number 1 for matrices. It's like the number 1 for matrices in that that matrix times any other matrix, in particular a column vector or column matrix, is itself. So v is the same as I times v. But what that allows us to now do is to factor out the vector v to the right, and we're left with a minus lambda times the identity matrix. Alright, and then we're saying that, well, that times the non-zero vector v has got to equal the 0 vector, and what our previous work has shown us is that the only way that's possible is if the determinant of this matrix a minus lambda times the identity is equal to 0. So we need to write that out each time we want to find eigenvalues for our given matrix. We got to find this new matrix a minus lambda times the identity, take its determinant, set it equals 0, and solve. Alright, so let's put that into play now with this matrix here. 4, negative 2, 1, 1. Alright, so the first thing we want to do is write out the matrix a minus lambda times the identity. So what do we have? 4, negative 2. Oh, I got that wrong. 4, negative 2, 1, 1. And then it's minus lambda times the 2 by 2 identity matrix, which we get 1s down the main diagonal, 0s in the off diagonal. Now with this, you can do this faster. After you do this a couple times, you're going to multiply the scalar lambda to each number in that matrix, and that's going to give us 4, negative 2, 1, 1 minus lambda 0, 0, lambda. You can use a different letter besides lambda also, but that's just very customary in it's kind of historic to keep with that. Alright, and that's done in most books. That's not a 0 there. It's going to be negative 2 minus 0, which is negative 2, 1 minus 0, which is 1, and then the last one's going to be 1 minus lambda, and we don't know what lambda is, so the best thing we can do is write that down. Okay, so we wrote out our matrix a minus lambda times the identity. Now our next job is to take the determinant of that matrix, a minus lambda times the identity. Okay, so now what we do here is, I'm just going to highlight it first, multiply that down the main diagonal, and then subtract off the product of the off diagonal. Take off that highlighting now, and we get 4 minus lambda times 1 minus lambda minus 1 times negative 2. Alright, so every time we find or given a matrix and we're trying to find the eigenvalues, we have to go through that calculation right there. It's going to happen over and over and over again. Now, just multiply out this polynomial. We get 4 minus 4 lambda minus 1 lambda plus lambda squared, and then we're going to get plus 2. Reordering that in descending order, we're going to get lambda squared minus 5 lambda plus 6. Okay, now what we're going to do is then solve the equation that we get by setting that equal to 0. We can solve this by factoring with the quadratic formula. I'll just factor it out. So we're going to look for numbers that multiply to positive 6 and add up to negative 5, and we're going to say that those only two numbers that work are negative 2 and negative 3. Set each factor equals 0. Solve the resulting equation. We get that lambda is equal to, or lambda is equal to 3. All right, so we've got two eigenvalues. We're always going to come up with two, all right, in our first bit of work here. All right, and we're going to just label these. So I'm going to call the smaller one of these lambda 1. And in some of the homework, that's the way it's going to go. You have to label the first one, the smaller one, lambda 1. And lambda 2, we're going to call 3. Okay, so we've got our eigenvalues. Now we have to find the corresponding eigenvectors. All right, how do we do that? So we'll start with lambda 1. All right, now what we got to do here is we are going to look for an associated eigenvector, which we're going to call capital V1. Now, what is this vector? We don't know yet, so we're just going to call it xy. Right? So it's a vertical vector we're looking for. It's a vertical matrix or a vertical vector, column vector, and we got to find that vector. So we need to find that vector V1 such that A times V1 is going to equal lambda 1 times V1, which is going to be 2 times V1, which is xy. So the right hand side is going to be the vector, after we do the scalar multiplication, 2x, 2y. Now we got to bring back the matrix A. The matrix A for our example was 4, negative 2, 1, 1. We're going to multiply that by the vector xy and then set that equal to 2x, 2y. Okay, now doing the matrix multiplication here, as we've talked about in some of our previous work, that's going to give us the vector 4x minus 2y. Keep in mind we multiply the row by the column. Okay, take that off now. And then likewise, we're going to multiply the row by the column here. So 1 times x plus 1 times y. Right, and that's going to go in our second entry. So it's going to be x plus y there. And that's going to equal over on the right-hand side 2x, 2y. Okay, from here, what we're going to do is then just set each component equal. So 4x minus 2y is equal to 2x, and x plus y is going to equal 2y. All right, now, this system is what is going to give us what is going to help us determine what the corresponding eigenvector is to the eigenvalue lambda 1 being 2. Now, this happens in different ways for different matrices, but this system of equations is going to determine what the possible eigenvectors could be. All right, let's see what happens in this case. So for this first one, what we're going to do, I'm going to look at that first equation. I'm just going to copy it over here. Let's get the x's on one side and the numbers on the other. So I'm going to add 2y to both sides, subtract 2x from both sides. The equation is going to give me 2x is going to equal 2y. If we divide both sides by 2, we would get y is equal x there. All right, now the second equation in here, if we just subtract x from both sides, we'll be able to isolate y, and that's going to give us, and that's going to be our two equations, so we're going to have a system of equations there. And then if we do that, we're also going to get y is equal to x. So both equations tell us the same thing. They restrict the relationship between the components of the vector v1 that we're looking for. Okay, that's what that system tells us. So all we want to find is some non-zero vector v1 that satisfies that relationship. All right, now we can just say in this case, pick any number we want to besides 0. As long as we don't pick 0, we're going to be okay. So let's just let x equal 1. If we let x equals 1, y is equal to 1. So our corresponding eigenvector v1 is going to be the vector 1, 1. You don't have to pick x equals 1. That's just the easiest possibility. All right, so that takes care of the first one. I've done a little bit of the writing for the second eigenvalue. Remember, this other eigenvalue was lambda 2 is equal to 3. So we want to find some non-zero vector we're going to call capital V2 such that A times V2 is equal to 3 times V2. So we take the matrix A, multiply it by that unknown vector, all right, and then set that equal to 3 times that vector. That leads us to this system of two equations, two unknowns we have right here. And then we isolate one of the variables in these equations. Now, if we subtract 3x and add 2y to both sides, we're going to get the equation x equals 2y. If we, in this case, the second equation, just subtract y from both sides, we get the same result. So we're led to the same equation for both of these ones here. And just for time's sake, I've put the result down below. We're just going to pick y to be 1 and if we do that, we get the vector 2, 1. So what does that mean for us? All right, that's our corresponding eigenvalue, eigenvector pair. All right, so in this case, we had lambda 2 to be 3, and that gave us v2, which came out to 2, 1. All right, so that's our first example in dealing with finding an eigenvalue, eigenvector pair.